this is a work that we're trying to understand the score-based generative models using the Wasserstein Proximal operators. So this is collaborations with Benjamin and John. You see the same picture in the morning with John from Brown Universities, Marcus from UMass Amherst, and Wu Chen from South Carolina, and my PhD advisor from UCLA here. So I think all the ingredients has been talked about, but just for complete pictures, I will go through everything again here. So generative models has been very popular. I mean, the workshop is having this keyword sampling as the first one, right? So it has been widely applied to image generations, recently video generations, and also for a more serious scientific research. So ultimate goals over here for generative models is if you are given a bunch of samples from some unknown distributions, we want to generate more samples from the same distributions. See if I have a bunch of pictures of cats, I want more pictures of cats from here by doing generative models. But in the same time, I don't want to see the exact same pictures I already have. I want something new from here. So this is a very popular areas, and there's lots of expertise in the room here using different approach such as GANs, normalizing flows, all these different, also diffusion models, different types of approach. So today we are going to just focus on the so-called diffusion-based generative models. So the diffusion-based generative models, so the pictures, the videos taken from Song Yang's blog. So what happened is if you took a very clean image and you keep adding noise to it, add noise till it's purely blur, like it's purely noisy. And then the reverse process is starting from this purely noise image, you start to denoising until you get the satisfied pictures. So if you think about a data point, the picture is a data point in some high dimensions. And then adding noise is like we are trying to apply like a diffusion process. Over here, it sounds like the reverse stage, right? We are trying to reverse like a heat equations, which is really like the first PD class we have that you cannot reverse a heat equations over here. But the score-based generative models, that's something more than that. So as we written down over here, the forward process is basically a forward SDEs. There you are trying to add noise to the clean data until it's purely noised. Yeah. And then for this reverse process, we will do more things more than just we are not reversing a heat equation, but instead we are running a drift diffusion reverse SDE with the drift. And this drift term is highlighted over here, referred as score functions, which is taken as a gradient of the log of the probability densities of the data set. So the idea behind this score-based generative model is if we learn or we are able to approximate the score functions at each time step for any arbitrary feature, the x, then we can just samples from random noise. That is, we can just pick a noise and then run this reverse SDE process with these known score functions. So typically what we implement this is to train neural networks to minimizing, for example, some score matching loss functions to approximate the score, and then we can do this generative process, generating samples from theirs. Okay, so this is a brief introduction of score-based generative models, and I'm just going to jump ahead to highlight what we are trying to do in this work. So in this work, we're trying to characterize this score-based generative models with as a Wasserstein Proximal, more precisely, regularized Wasserstein Proximal operator of cross-entropies. And this will, the regularized Wasserstein Proximal operator will connect with mean field games, which equivalent to alternative formulation of score-based generative models. And from there, we did experimental formulations, like kernel formulations for score-based generative models. Using all those ingredients. And what we find is that the connection we made explain the memorization effects of the score-based generative models. And in particular, what we took from there is we have a slightly practical models that can generalize vectors with limited, with limited experiments justified, we're able to using this mathematical informed structures to train faster with less data. Okay. Yeah. So next, I'm going to just, I know everyone probably here in this room are familiar with this optimal transport since it's just after Alex talks. But just for complete storage, I will still walk through everything from here. So this Wasserstein matrix defines the distance between probability distributions, and this is also known as the Earth mover distance. How you can effectively move an Earth of a shape of mu to the k of the nu with a certain cost function c of x, y over here. So this kind of movements cost will be used to describe the distance between these two probability distributions. And this kind of problem was first studied by Monge to describe to solve this really soil transportation problems. And the contour-rich formulations allow us to split the mass, and we have applications to plywood industries, and it has widely applications in all these areas. And one of my favorites is I'm training from UCLA with this PD backgrounds. My favorite formulation is the so-called Brenner-Move formulations, which you have already seen in the previous several talks, which is talk about how to using this computational fluid formulation to quantify this to describe this mass transport process. So what happened is we are not trying to find a one-to-one map to split to move the mass. Instead, we want to find a velocity field v of xt that is going to flow a density from distribution mu of x to the distribution v of x in a time horizon 1. So this formulation gives us this very nice PD constraint optimization problems, where the objective function is basically in the Wasserstein 2 matrix. We're talking about moving the kinetic energy we use to move the mass, and the constraint over here is a Fokker-Planck equations with boundary conditions rho 0 and the rho at terminal time given as the target distributions. Okay. And then this will next is to introduce this Wasserstein proximal operators. It's basically like proximal operators in the probability space. So it can be written in the following form as we are trying to find a distribution such that it's going to minimize the function with respect to q of x with a proximal term over here is using this Wasserstein matrix. So if we take this v of x, so we took a special case with a linear functional with respect to our unknown function q of x. So if v of x is some negative log pi of x of some density distribution pi, so this first term v of x q of x terms give us basically a cross-entropy terms. So these proximal operators can be understand as we're trying to redistribution the mass to this reference distribution pi of x, but we are also going to consider the transportation cost from current distributions to the from this row 0 to the target distributions. So this kind of Wasserstein proximal operators has been studied in other generative models as well. So the optimal transport flow by Lawrence, this is basically a Wasserstein 2 proximal operators of the KL divergence. And I think in tomorrow's next few days talks, Marcos and Lucas, they will talk about the F gamma divergence, which is going to be Wasserstein proximal operators or Wasserstein 1 distance connected to F divergence. So this is actually a very rich areas. So, but I'm going to pull back a little bit to look at constraint optimization problems perspectives. So solving a Wasserstein proximal operator is not an easy task. So if I view it as it's going to be optimization problems in the probability space. But what we can do is we can utilize the Bernier-Bernoulli fluid formulation of optimal transport. There we can recast this Wasserstein proximal operator, this optimization task, as a constraint optimization problems. So the constraint optimization problems will share the very similar form as the Bernier-Bernoulli OT transportation forms, but what you will see is in this optimization problems, we have an extra term which stands for the is basically the cost function, the potential, the v of x regarding the target distributions. And for these constraints, we are no longer trying to do optimal transport with the target row. Instead, we are only given some initial distribution at t equals 0. So this actually becomes a variation of formulations. Okay, so from here, so this is a constraint optimization problems. We can always look at its first order optimality conditions, so which will give us this very nice couple systems where the first equation is a Hamilton-Jacobi equations, which it show up in the first slides. I mean the first talk from Monday, and over here. And then we still have these Fokker-Planck equations, but there's Fokker-Planck equations. The transport term is given by this velocity field from this control, the control gradient of U terms. And the special thing is about this couple system is this is a forward, backward different PD systems. U equations runs backward in times, and rho Fokker-Planck equation runs forward in time. And this is actually like a typical mean field games problems that we have seen in previous talks. I think Ron just talked this morning. Okay, yeah. Yes. And this is actually the simple mean field game if we don't consider any interactions among the agents. So what we did over here is actually so firstly it was a first order PDEs, and we introduce a regularized Wasserstein proximal operator through this dynamic formulations. So what we did is we add viscosity terms to this continuity equations over here. So it is the same objective functions which quantifies a kinetic energies that you pay to move the mass, and the terminal terms that accounts for the terminal term how far. If you think about the KL term, it's a cross entropy of the terminal distribution with respect to some reference. And then subject to a constraint, subject to a Fokker-Planck equations. But here now we have the viscosities over here. So we refer this one as a regularized Wasserstein proximal operators, the solution to this one. And actually what we have is from this formulation by adding these viscosities, we obtain closed form formulations, which allows to get a fast computations for these Wasserstein Proximal operators. I think in future talk, in later talk, Fuchen is going to talk to you more about this. Yeah. So from there, let me just elaborate more about this regularized Wasserstein Proximal operators. So this is still can be viewed as a constraint optimization problems, and the optimality conditions will be similar forms, but instead of having the first order coupled systems of HJ equations and Fokker-Planck equations, now we had viscosity terms in both equations, and one equation forward in time, backward. One equation runs backward in time, forward in times. So the closed form formulation really comes from the fact that if we apply log transforms to this U function, this HJ equations, and this equation actually can be rewrite as the heat equations. And with the heat equations, if you have initial conditions, you can write down the solution exactly, and then we plug in back, and we are able to get the solution of the U over here. Yeah, and the similar techniques has been used in other literature on this reference I added on this Wasserstein Proximal operators for Schrödinger bridge problems. Yes. Okay. Yeah. So here I want to make the connections from this score-based generative models with respect to this regularized Wasserstein Proximal operators. So we will stay with this cross-entropy terms, which means that we will choose this v of x as a negative of the log of pi of x, with pi of x being some reference metric. And we will look at our regularized Wasserstein Proximal operators as we have with these parameters. So sigma squared over 2 is the original beta, and the capital, the previous step size tau will become this capital T. Yeah. And now if we apply this Cole-Hopf transform, and then we do a time reparameterization of the with this introduce this S. So the original the coupled systems for this regularized Wasserstein Proximal operators can be written in these following forms, where the first equation is essentially the heat equations with the initial conditions given, and then this the Fokker-Planck equations. If you recall, the Fokker-Planck equation, the drift term was given by this gradient of U. Now we got the explicit expressions, and it is the sigma squared times gradient of log of etas. Yeah. So, and if I put it over here already. So if we try to compare with what is happening in the score-based generative models, so this actually goes degenerate to the basic case that for this score-based for this forward SDE process, you only consider purely diffusion. And then for this reverse process, you have a reverse SD process with the drift terms, and this drift terms is given by the score functions, which corresponding to what we have over here in this in the form of the score with the gradient of the log of the densities. Okay. Yes. So if we trying to write the score-based generative models in the more compact forms, and I will denote this pi hat as the samples I'm given. So we can view this score-based generative model as a forward-backward coupled with this Wasserstein Proximal operators, and it actually reviews this noisy and denoisy natures of the score-based generative models. And another thing we actually got is since we are able to write down the solution to the Wasserstein Proximal operators, the regularized Wasserstein Proximal operators, we are also able to write down the exact score functions for this types of generative this basic score-based generative model where the forward process is just purely diffusions, and this is just the kernel formulations with and where this is this G of T stands for just the heat kernels. Yeah. And I still remember by that time we thought, okay, since we get of course formula, we are done and we no longer need to train for a score, and we can just plug into formula and run the backwards reverse, the reverse process. But actually, what we eventually realized with some simple data set, we realized when we have a very nice score functions, we no longer get new samples. We got only overfit. That means all the samples we're trying to generate new samples, but every time we are getting dragged to the drift term get us dragged to where the original sample was. Yeah. So instead, we thought, okay, probably not a Gaussian, like a purely Gaussian kernels with a homogeneous diffusion process, but instead, we should consider a generalized empirical distributions with Gaussian kernels where the local covariance should be driven by the data. So what we would propose is over here, instead of doing having this IID samples, we should diffuse the data samples a little bit with a learned local covariance matrix driven by the data. And what we did eventually is actually we use the neural networks to learn the stochastic decomposition of the covariance kernels and apply it here. So basically what we took is the training scheme is to enforce the terminal conditions of the HG equations we have, so which is basically equivalent to the implicit score matching at the terminal times. And what we are doing here is trying to learn a local covariance matrix is akin to manifold learnings. And here is probably a more illustrative result. So originally, if we just took these HJ equations and we run this reverse diffusion process with this basically analytical kernels. So what we will see is we will get exact the original samples, and it will just basically be overfit. So they call it memorization. But with this the new proposed approach where we're trying to learn generalized kernels over here, we're able, and then we do this reverse diffusion process using these kernels, we're able to see a better generalization result. So what we are trying to say is, okay, we are able to learn a low-dimensional representation space by enforcing the proper terminal conditions of the equations in one step. Yeah, so I apologize, we only have low-dimension examples over here. So what I'm showing here is the ground truth data set with denoising score matching methods with different training epochs and our training approach. So on this low-dimensional data set, what we can see is we're able to learn better with this kind of distributions and also train faster. But yeah, with this basically the kernel methods. And another thing we're trying to see is to look at this low-dimensional data manifold. Is we took a 3-dimensional Swiss-row examples and noisily embedded it into 6 dimensions and directly try to learn local covariance matrix for this data set. And the result is actually it looks good to us. Yeah. Yeah, and the other thing we're trying to zoom in is for this two-dimensional data, we look at the local covariance matrix, and we're trying to the local covariance matrix we learned, and then we try to plot as this ellipse, and we saw they're very nicely aligned with the data distributions we have. Yeah. I thought. Okay. Yeah. So yeah, I think I have a very short talks. So the takeaway is in this work we're trying to make connections between Wasserstein Proximal regularized Wasserstein Proximal operators with the score-based generative models, and in this case. We are able to, for certain data, we are able to have, with this proper choice of kernels by solving HG equations, we are able to resolve this kind of memorization effect and train faster with less data. And in this case, because it's essentially we are doing like trying to learn the local covariance matrix, we no longer need to do this SDE simulations to reverse. Basically, we just sample using this kernel we already know, and we are trying to, but the limitation at this point is we know that this is as long as we want to directly learn the local covariance matrix, it's not going to be scalable. So this should be something that more directly tackle the intrinsic dimension of the data and trying to learning this local covariance from theirs. Yeah, that's all for the talk I have. Thank you.